In section 5.2, we saw that computing definite integrals using the definition of a definite integral as a limit of a Riemann sum can sometimes be very long and complicated. In this section, we're going to see that there's a much simpler approach to calculating definite integrals, and it involves the antiderivatives that we saw in the last chapter. This is going to form part of what's called the fundamental theorem of calculus, but for the moment, let's just focus on learning this new technique for calculating definite integrals. The technique is called the evaluation theorem. The evaluation theorem is given in the box here. It says that if we want to calculate this definite integral of the function f of x from a to b, then all we need to do is take any antiderivative, denoted here by capital F, and evaluate the antiderivative at b and subtract from that the antiderivative at a. In other words, the definite integral of the function f of x from a to b can be found by first calculating an antiderivative and then looking at the difference of this antiderivative when evaluated at the two endpoints of the interval. This provides a remarkably simple and much more powerful way for calculating definite integrals, and we're going to see that in the next few examples. A couple of other things before we move on and look at examples, though. There's some notation that we need to introduce. Remembering that capital F of x represents an antiderivative of lowercase f of x, when we apply the evaluation theorem, we sometimes use this notation here. The antiderivative, uppercase f of x, evaluated at b minus the antiderivative evaluated at a, is sometimes written like this. And so we can write the evaluation theorem from the above box in this slightly more compact form here. A couple of other common notations that are also sometimes used for the right-hand side of the evaluation theorem are given here. Let's now work through a simple example. Evaluate the definite integral of the function e to the x from x equals 1 to x equals 3. So to apply the evaluation theorem, we first need an antiderivative of the integrand here, which is e to the x. An antiderivative of e to the x is just e to the x itself, and so we can then use the evaluation theorem as follows. The definite integral of e to the x from 1 to 3 is equal to the antiderivative e to the x evaluated at 3 minus the antiderivative e to the x evaluated at 1. That's what this notation here means, and written out more explicitly we get this quantity here. Here's another example, example 5.3.2 from the textbook. Find the area under the cosine curve from 0 to b, where b lies in the interval from 0 to pi over 2. The figure here illustrates what we're looking for. We've got the function y equals cos x, and we're interested in the area under this function from 0 to b, where b lies somewhere in this interval from 0 to 2 pi. An antiderivative of cos x is sine x, and so now we can use this in the evaluation theorem. The area under the curve, capital A, is the integral from 0 to b of the function cos x. And applying the evaluation theorem, we have the antiderivative sine x, and this is evaluated at b minus sine x evaluated at 0. That's what this notation here means. Written out explicitly, we have it here, sine b minus sine 0. And of course, the sine of 0 is 0, and so we're left with the quantity sine b. Now in the figure above, when b equals pi over 2, we get an area of 1 because the sine of pi over 2 is 1. Let's do one final example, and in this example we'll return to one we looked at previously using the limit of Riemann sums to illustrate how this new approach for calculating definite integrals is much simpler than our previous approach. An example we looked at previously asked us to calculate the definite integral from 0 to 1 of the function x squared. And we did that by first setting up a Riemann sum where there were n approximating rectangles, and then we looked at the limit as the number of these approximating rectangles went to infinity. Now we can evaluate this definite integral using the evaluation theorem. The first thing we need to do is find an antiderivative of the function x squared. Well, an antiderivative of the function x squared is just 1/3 x to the power of 3, and we can verify that by taking its derivative to make sure that it does in fact equal x squared. And then we want to evaluate this antiderivative at 1 and subtract the value of this antiderivative at 0. So in other words, this is going to be 1/3 1 to the power of 3 minus 1/3 0 to the power of 3. Of course, this is 0, and so we're left with 1/3, which is exactly the answer we got previously, but you can see that using the evaluation theorem provides a much more direct and fast route to this answer.